Well, you see, I've already discussed about the equation of mass conservation. Basically, I've talked about all the equations of stellar structure, but I feel that after our derivations and various discussions, I have to sometimes stress, probably again, on certain important points, and this is so that you understand the basic principle. I would like to stress again on some of the principles related to these equations of stellar structure as well as their applications. Now, as I was saying, I have already talked about the equation of mass conservation, all that. Now, today I'll try to talk about some of the related principles and applications on other equations. So let's see. Let's start with the equation for hydrostatic equilibrium. Okay, so the first thing that I would like to talk about is what can happen. What are the consequences if there is a slight deviation from hydrostatic equilibrium? This I would like to talk about now, and after that I will talk about what will happen if there is no hydrostatic equilibrium at all. Okay, so let's first start with a small deviation. Let's see. Now here you can see, so this is your equation of hydrostatic equilibrium, right? And you do note that dpdr is negative, and this is why, because as r increases, the distance from the center increases, the pressure decreases, and this is in fact necessary for the pressure force to counterbalance the gravitational force. Now let us consider a small deviation from hydrostatic equilibrium. So let's suppose a small volume element at a position r be accelerated inwards. So r is somewhat decreased from its original value. Then what will happen is that since r is decreasing, so we are saying that suppose the star contracts from its hydrostatic equilibrium condition, then what will happen is that this equation 1 will become like this. How? You see, as r decreases, 1 by r square increases. So this side becomes greater. Okay. So next thing is that let's talk about the acceleration towards the stellar center. Well, let us use the equation of motion, which we have again derived in our class previously, and upon doing this we will get this relation over here. And suppose this acceleration is constant over a period of time t, in which you see the gas moves through a fraction alpha r of the stellar radius r. I am assuming that alpha is very less than 1. Then you remember your rectilinear motion class 11 principle, S is equal to ut plus half at square. So if I use that, our S is basically alpha s r, and since it starts from 0 velocity, I mean at rest, so u is equal to 0, and we have just half at square, and from here you see we get a value of t square. Fine. So what next? What next is that now we are going to do a very drastic approximation, very drastic indeed. So you see, I am just taking over here average values at the center. It's funny, but yes, I can take it, and let's see what do I get from that. So r is equal to half of the value of the radius, and similarly mass is half of the value of the entire mass of the star. And if I use this in this previous expression, then I get this value of t square. Now let us write this equation in terms of the solar quantities, and if we do so, then you can check yourself that we will get this relation for the time. And let us now assume that, so So let us now assume 1% deviation from hydrostatic equilibrium. So what are the things that we have assumed? Till now, we have assumed a small deviation, that's okay. But this is the first adaptation that we did, average values. Next, we are now assuming 1% deviation from hydrostatic equilibrium. So this means this value is approximately equal to 1%, means 0.99 multiplied by this. So that F is approximately equal to 0.01. And so what's the consequence? You say, considering a fraction of about 10% of the solar radius. Suppose the mass fragment moves 10%. So alpha is equal to 0.1. Then what we get is this value of T. For the sun, what will it be? This entire thing will be 1. R is equal to R solar, M is equal to M is equal to M solar. And so for the sun, this is just the value, which is 85 minutes. So a deviation from hydrostatic equilibrium of just 1% would affect a considerable fraction of solar radius of about 10% in a very short time of approximately 85 minutes. But do we see such a thing? Do you see the variation in luminosity all of a sudden in the daytime? Has anyone ever observed such a thing throughout history, throughout the human civilization period? No. We have never had any such evidence that the sun has, and so this means that the sun has been stable for a much longer period. And so if indeed there are deviations, then it must be much smaller than your 1%. Okay, so this is what I would like to discuss with you regarding the deviation from hydrostatic equilibrium. Next, suppose there is no hydrostatic equilibrium, there is no pressure support, then what? Now you see, basically, what is a star? A star is a sphere of gas that is held together by self-gravity and is balanced against collapse by pressure gradient. But who is the real reason for this balance? It is actually the fusion. So star must satisfy two criteria. One is gravitationally bound, another is your fusion reactions must be initiated in the core. Okay, now so what we are going to do now, since I am going to talk about the absence of pressure support, we are going to calculate the free fall time scale of the sun, our nearest star. Basically, the time that would take to collapse to a point. Why? Come on, I am talking about no pressure support. So if there is no pressure support, who is going to go against gravity? No one. And the gravity will just crush the entirety of the mass of the sun to a single point. Okay, so this is what we are going to talk about, and we are going to estimate the time taken for such an event. Time taken for the entire sun to be collapsed to a single point. Okay, so let's again start. Let us consider a small mass element dm which is at rest initially at a radius r0. What's the potential energy? Of course, this is the potential energy. Where what is this mr0? This is basically the mass interior to r0. Now let us apply our good old conservation of energy. Okay, so what we get is the velocity of the element as it falls towards the center as this. Now here this is a reduction. I have cut some parts over here. You can check. What is it? Half mv square. Remember? So m is missing. I have just cut it out and I have just written the entire velocity terms only. Now you see the initial total energy when dm is at rest is du at r is equal to r0. But as it starts falling towards the center, both kinetic and potential changes. And so r, what is the change? What is the range of its change? So it changes from r0 to 0. That is when the collapse happens to the point. Okay, so another very interesting point is that even in this entire discussion, we are assuming that the amount of the infalling matter which is interior to R0, it remains constant. Of course, this is not entirely correct, but let's just do an approximation and see what we get. Now, separating the variables and integrating, we get the T effective, T free fall time like this. And if you do the integration, while the value is this pi by 2 and considering the density, then you get this value for free fall time scale. Note that this is dependent on 1 by rho average to the power half. Okay. Now what's the reason? So basically for a given total mass m, if the density is much more, then this means the star is much more compact, the radius is smaller. So it, of course, it will take smaller time to collapse to the point, and that's why the free fall time scale is smaller if density is large. Okay, now what's the value for our sun? So if you put in the parameters of the sun, as you can see I have done over here, then you will see that it comes out to be approximately 30 minutes. So this means that without the pressure support, the sun would collapse to a point within half an hour. Of course, this is not happening, right? And we are very lucky that it is not happening. Anyway, it cannot even happen because of the pressure support. And even if pressure support is not there, there is also your degeneracy pressure. But anyway, that's other talk. Okay, now suppose I ask you, what are the most fundamental lessons that we have learned from hydrostatic equilibrium? Okay, now you see, I have shown you that we can derive the value of the Tc, that is core temperature of the star, by using this hydrostatic equilibrium. Note that we can do this derivation without saying anything about energy generation or energy transport, right? And what have we done while doing this derivation? We have just used the observed radius of the sun and also the observed mass of the sun. That's just what we have used to do this. This is the first very important lesson. The next one is that which follows from here. We observed that Tc can be very high, of the order of 10 to the power 7 Kelvin or so. And what does this mean? This means that the central temperatures, high Tc, allows nuclear fusion. So this is the second very interesting point that we learned. You must remember this. Okay, now so we have talked about this hydrostatic equilibrium. Now let me spend some time on the equation of mass conservation. Some things I have already discussed in class. Now let me just write it down. Equation of mass conservation. So basically our equation is like this: dn dr is equal to 4 pi r square into rho r. Right. Now what I am going to do is I am going to discuss about mass loss in stars. Now you see, many stars, they lose mass continuously to the interstellar medium. Okay, lose mass stars with velocities around approximately 10 kilometer per second to few thousands kilometer per second. Okay, or of the order of or larger than your stellar escape velocity. Now, what does this mean? Well, this means that the hydrostatic equilibrium condition is no longer valid, at least in the external layers of the star, where the pressure force dominates over the gravity force. Okay, so star, if this is the star, we are talking about the surface, so mass getting out. Of course, this is due to the fact that pressure force is dominating the gravitational force in the external layers. Now you see, we can use this equation of continuity and obtain a very simple expression for the mass loss. Rate, basically rate of mass loss in stars per unit time. Let's see. So basically we have dm dr is equal to 4 pi r square rho into t, right? So we can write, what is the mass loss? Mass loss is basically rate of mass loss is basically m dot or dm dt. So if we use this equation, what we get is just this 4 pi r square rho r into vr, right? Where vr is r dot is just the gas expansion velocity. So if you put in the values of the r that we just talked about previously, then you will see that we get mass loss having range from say 10 to the power minus 14 solar mass per year, which is 6 into 10 to the power 11 grams per second for Sun, to of the order of 10 to the power minus 5 solar mass per year, and that is around 6 into 10 to the power 21 gram per second. This is for very hot stars. Okay, so this is quite interesting, although a very simple application of the equation of continuity. Okay, so related to this equation of mass conservation is your equation of energy conservation, right? So you see, similarly to the mathematical development regarding the conservation of mass, we can also write down the quantity of energy per second, basically luminosity, which is generated inside a spherical shell between radii r and r plus dr, and we can write it down like this: dlr is equal to 4 pi r square rho r epsilon r dr, where you see this is basically your local density, right? And this term rho r into epsilon r, it represents basically energy per unit time per unit volume generated at radius r. Now this equation we can write in this form: dlr dr is equal to 4 pi r square rho r into epsilon r, right? And this is the energy conservation equation, or sometimes also known as energy equation. Now its integration, given that we know rho r and epsilon r, leads to the luminosity at a particular radius. So this leads to this luminosity L at a particular radius r, dr. Okay. Now you see this equation. Let's concentrate over here. Let's consider the right hand side of this equation. Now you see the right hand side is either positive or 0, which means that dlr dr is greater than or equal to 0. So this means that luminosity increases with distance r. So Lr increases with r increase. Right. Now, not surprisingly, this equation shows that if nuclear energy production rate increases, right, this one, so does the luminosity. If this one increases, so does the luminosity. Now, we already discussed that the fusion takes place in the central regions of the star, right? So fusion takes place in central regions of star. So what can you say? Consequently, what we can say is that epsilon is equal to 0 in the exterior regions. And so, dl/dr is also equal to 0 in exterior regions. Now, in these outer regions of the star, the luminosity is therefore constant. So, outer regions, luminosity is constant and equals L, which is the total luminosity of star. Okay, now let me again concentrate on this equation and let's see if we can get an estimate of this energy production rate for our sun. Let's see. So, estimate. So, let us assume again order of magnitudes, estimate. So, let dl, so this is order of magnitude estimate for energy production rate. So, let dl be L, dr be R, and rho be your average density rho. Then we can write from this equation of energy conservation, this form, we can write epsilon is approximately equal to L by 4 pi r cube rho average, or this is just L by 3m. Now if we take the numerical values for the sun, then we will get, you will see for the sun we get approximately 0.6 erg per gram per second, and so we can write for other stars epsilon as 0.6 L by L solar divided by M solar erg per gram per second. Now, generally for main sequence stars, this value of epsilon, this lies between 10 to the power 6 to 10 to the power minus 1. Again, the units is erg per gram per second. This is important, you must remember. Interestingly, it is also possible to do a sort of scaling and get an dependence of this energy production rate on temperature. Let me show you how. So what I want to do is, again, using only scaling and order of magnitude, we would like to see the dependence of energy generation rate on temperature. Now we know that epsilon is proportional to L by M, right? And we also know that L is proportional to N, where N is of the order of 3. Fine. Now since T is proportional to M by R and M is proportional to R cube density, remember? So this means that we have epsilon is proportional to M square is proportional to T square R square, or this means epsilon is proportional to M square is proportional to R to the power 6. So this means T is proportional to R square, and thus epsilon over here is proportional to T cube. Okay, just let me again show this to you. You see, epsilon is proportional to L by M, and this is the relation. So we directly get epsilon is proportional to 3 minus 1, that is 2, right? And so M square. Now from here we get epsilon is proportional to T square R square, right? Next again, epsilon is proportional to M square here, and from this relation M is equal to what? Density is equal to mass by volume. So mass is equal to density into volume. For constant density, we have mass is proportional to volume, or 4 by 3 R cube. So mass is proportional to R cube. And so this relation, it gives me just M square is proportional to R to the power 6. And now from these two relations we get, basically from these two scalings we get T is proportional to R square. Okay, so this means, considering that epsilon is proportional to R to the power 6 and T is proportional to R square, so this means that we get epsilon is proportional to T cube. Again, this is an order of magnitude estimate using scaling. Well, you will see later that the value of luminosity is fixed by the energy transfer processes and particularly by the temperature gradient in the stellar interior. Now you see, if we divide the equation of mass conservation by continuity equation, so dividing equation of energy conservation by continuity equation, then we will get dl dm is equal to epsilon. This is basically the Lagrangian form of, sometimes it is said, this is the Lagrangian form of the equation of motion. And this equation shows that the energy lost by the star must be compensated by the energy produced by nuclear reaction. Now you see, this equation in fact can be generalized. It can be generalized to include, number one, neutrino loss, neutrino energy losses, and number two, occurrence of non-stationary processes. Right. Now, regarding neutrinos, you know they are produced by the same fusion reactions that generate the stellar energy, as well as by other reactions. Now, since the neutrino interaction cross-section with the stellar matter is very low, they are able to go through the whole of the star and escape to the interstellar medium, so that the part of the stellar energy is carried by them. Now, the energy of the neutrinos per unit time is basically neutrino luminosity, which is defined as L nu 0 to m epsilon nu dm, where this epsilon nu is the energy per unit mass lost by the stellar matter per second as neutrinos, and this is neutrino luminosity. Okay, now what about non-stationary processes? Now in the non-stationary cases, you see there are changes in the internal energy of the expanding or contracting layers, even in the absence of nuclear reactions. And in this case, an additional energy term is included, so that we can write dl dm is equal to epsilon minus epsilon nu plus epsilon g. Okay, so we have discussed about hydrostatic equilibrium, and then we have discussed about equation of continuity, and finally about this equation of energy conservation. Yeah. Okay, now before I finish, I would like to talk about this part, this mass luminosity relation. Now you see, it is quite instructive to see that this observed relationship can be understood qualitatively using the help of only two stellar structure equations. One is hydrostatic equilibrium and another is your radiative heat transport equation. Okay, now let's see. And the most important thing is that we can do this even without any knowledge about the origin of the energy needed to maintain L. So let me write it down. So what we would like to do is we would like to explain L proportional to m to the power say n, and the or experimentally value is around this or so. And interestingly, we can do this using hydrostatic equilibrium and radiative transport equation. And the most important point is that without any knowledge about the origin of the energy needed to maintain the luminosity L. Now the mere fact that most stars are stable, it tells us that such a relation must exist. Now the argument goes as follows. Generally, we can say that on an average the density must be proportional to the mass divided by volume of the star. That is, rho is proportional to m by r cube. Okay, now what about hydrostatic equilibrium? Hydrostatic equilibrium, basically it demands dp dr is equal to minus d rho or minus gm by r square into rho, right? So we can roughly approximately write it as, you see, p by r approximately equal to gm by r square into m by r cube. So this means that p is proportional to m square by r to the power 4. Now making use of the equation of state, so equation of state, which is p is equal to r by mu rho into T. So using this we can get temperature T proportional to P by rho or proportional to m square by r to the power 4 into r cube by m, or this is proportional to m by r. Remember, we used this relation previously as well, T proportional to m by r. Now if we use this in our previous equation of the radiative transport, then you will see what we get. Radiative transport equation, then we will get L is proportional to minus r square t cube dt dr to 1 by kappa, or this is equal to minus t cube by kappa into rho dt dr into r square. Yes, this should be rho into kappa over here. Yeah. Now assuming that kappa remains constant, kappa is approximately constant, then using the density, using this density form and this form over here, which is T proportional to m by r, you will see that we will get finally L proportional to m cube by r cube by m by r square into r square. So you see, T is proportional to m by r, so T cube is m cube by r cube. Then we have this mass over here, density, mass by volume r cube. Then dTtr, if T is proportional to m by r, then dTtr will be proportional to m by r square. And then finally this r square. And from here, we get your proportionality of m proportional to m cube. Well, you can also replace dt dr by minus Tc by r, which is the central temperature, divided by the radius. And finally, we get this value, L proportional to n cube, which is basically the mass luminosity relation corresponding to the observed relation that we talked about previously. Yeah, here. Okay, so what did we learn? Basically, you see that we have derived this 3 power by assuming that kappa is independent of pressure, temperature. Okay, and so we assume P is proportional to gas pressure. One thing is that our calculations tell us that temperature in the interior is determined by the hydrostatic equilibrium, which we have also previously seen, and that basically determines the luminosity. When the temperature at the surface is very close to 0, then the average temperature gradient is dt dr is approximately equal to minus Tc by r. This we used, right? Now once your opacity kappa is known, the radiative heat transport determines how much energy is transported to the surface, and this is of course the luminosity. So the larger the central temperature and the smaller the opacity, the easier the heat transport and larger will be the what? Luminosity. Remember? Yes, from this relation we can see.